This set of slides relates to the second double lesson in kinetics for year 13. We are going to kick off with a practical. We're going to be looking at the reaction of potassium iodide with hydrogen peroxide. Okay, so it's a redox reaction. Okay, so you have the iodide being losing electrons, so it's being oxidized to iodine, and the hydrogen peroxide is being reduced. So I've got the right way around. So there we go. If you can actually take all of the spectator ions out of the equation, you've got 2I minus 2H plus going with H2O going to iodine and water. You are going to monitor this in a very similar way to the iodine clock reaction using starch to determine the rate of the rate law of the particular reaction. So the generalities there. So you remember we looked at rate equals Ka to the power m and b to the power n. Okay, so here we go. We have got this same rate equation here with iodide, hydrogen peroxide, and acid with N, M, and P. Okay, and what we're going to do is we're going to retain the acid being constant. Okay, so we can then replace K with what we call K prime, where K prime equals K H plus the P, but we're keeping it as constant. So we're just focusing on iodide and hydrogen peroxide. What you're going to do in the reaction is you are going to look at 5 different experiments. So if you look overall, the total volume is going to remain the same. So the first 3, you are keeping the hydrogen peroxide the same. You are obviously keeping the acid the same because that's being stated that you're keeping the same. What you're changing is the concentration of potassium iodide, and you are increasing it. So you need to see what happens to the rate as you double and triple the concentration of potassium iodide. Okay, so simple clock reaction. To work out the rate with respect to hydrogen peroxide, okay, you've got experiments 3, 4, and 5 where you're keeping the potassium iodide at 12 mils. So keeping the concentration of that constant, and you are doubling and quadrupling the concentration of hydrogen peroxide. You're going to see what happens to the rate there. So that is the basic set of rate experiments that you need to be able to do at A2 level. The PSA you did during the summer sessions, which was the iodine clock reaction. This is just a very similar one. I didn't want to give you the same one again. Right, this is very much an extension beyond the A2 syllabus because as well as changing the concentration, there are some other additional experiments which I'm giving out to you, which are to change the temperature and to add a catalyst. So a little bit of additional content here about the Arrhenius constant. Okay, so what you find experimentally is that K, the log of hopefully I've done the maths. The log of K is proportional to the log of 1 over the temperature. Okay, so basically as you increase temperature, K will change in a expected and in an expected relationship. Okay, so what you can do is you can work out these Arrhenius constants. So we'll spend a bit of time on this with those who want to spend some time looking at this. If you want to know more, here's some Chem Guide stuff, which is also quite a nice little explanation. I've also posted a couple of things on the Google Classroom. Just out of interest, A depends on the frequency of collisions and their orientations. So this is what's different, why it's different for each reaction. Okay, because it's going to depend on the orientation of how they bump into each other, whether they're going to react or not. So this will be kind of a nice little extension for you. The other thing we're going to look at is the catalyst. So we're going to change catalyst, see what happens to the rate there. And there's also some calculations to do there. I can't remember off the top of my head what we're doing, but I will have a look at it ahead of the lesson tomorrow. So here's the specification link for the rest of the lesson. Understand that orders of reaction with respect to reactants can be used to provide information about the rate determining and limiting step of reaction. So this is polishing off the kinetics section, which should be fairly fast and furious. Hopefully this will make sense to you when I go through it in the lesson, otherwise I'll have to re-record this. So reactions take place using more than one step, quite often. Okay. So this one here, this is the bromate species, BrO3-, that should be a little 3. Why does this not do superscript bro 3-? There we go. Right, so in this case, what's happening is obviously the bromate 5 is going to bromine 0, okay, so high oxidation to low oxidation station, it is gaining electrons, okay. So this is taking place in various different steps, and there's going to be intermediates. So in a multi-step reaction, the slowest step is called the rate determining step. So imagine making a cup of tea. I am boiling the kettle, I am pouring the water onto the tea bag, and I'm letting it soak, and then I'm making my nice little cup of tea. So the rate determining step, well, everything kind of depends on how fast the kettle boils, because nothing else can happen until the kettle boils, and that's kind of a slow step at the beginning. So it's the same kind of concept with chemistry. So if you have a slow step at the beginning, that's going to be determining the rate that the rest of the steps can take place. And any steps after that won't really affect the rate of reactions, so they won't appear in the rate equation. So what does that mean? Right, we are going to imagine just this bit that's kind of slightly paled out here. We're imagining that we've got A and B and C joining together to make D and E. Okay, and it actually happens in 2 steps. So the first step is this step up here, so I'm going to call this step 1. Oops. Step 1, where A and C join together to make a new species X. Okay, and then what happens in that step 2 is that X reacts with B to get to the end point. Okay, so because this is the slow first step, this is the rate determining step. Nothing else can happen until this has happened. Okay, so it doesn't matter how much B is present, because as soon as X is made, B reacts with it to go to the end point. So the thing that actually is going to determine the rate, so rate will equal K A to the power N C to the power M. Okay, B does not appear in that rate equation there, because the rate is not dependent on the concentration of B. Okay, the step that is slowing down the whole reaction is this A plus C. Notice I haven't stuck in N's and M's here, because that's not necessarily obvious either from what we've got there. So it's always good to have a real life example. So this is the iodination of propanone. I mentioned this in the last presentation because this is a reaction that you can follow using colorimetry. Okay, so you got your nice little brown iodine solution, and you add it to propanone, and as it reacts with propanone, it becomes colourless, so you can see what's going on. So you can measure the rate by the colorimetry, and acid is the catalyst for the reaction. So we'll have a look at the steps for this. Right, so what's actually happening in this, and you're going to be doing some reaction mechanisms with Mrs. Tarry this term, so hopefully this will start to make even more sense once you've gone through that, is that the first step is actually taking your propanone here, this is your propanone, and you are protonating it. Okay, so what you will learn with Mrs. Tarry is that that oxygen has a lovely little lone pair, okay, that it likes to donate out to the hydrogen, okay, to make this protonated intermediate, okay. But as soon as this protonated intermediate is made, it doesn't look very stable because you don't see it a lot. You wouldn't have not seen that before, so you think, well, there must be something else happening next. So what happens then is that there is a rearrangement, okay. So you get your double bond, flipping around, okay, to create this double bond here between the 2 carbons, and then you are simply adding an iodine, okay, to that carbon double bond, okay. So in a very similar way, and then you are flipping the double bond back onto the oxygen. Okay, so don't worry too much about the mechanism of that right now. But the key point is that this is the first slow step, in that you've got the propanone adding to the acid. Okay, so nothing else can happen until the propanone has been added to the acid, which means that for the rate equation, okay, the rate is going to be equal to K, the rate constant, times your propanone. I'm just going to write that down because otherwise I'm making a mistake. Propanone to the M, and H plus to the N. okay, and that the iodine does not take part at all. So, in a sense, when you are looking at reaction rate kinetics experiments, it can actually teach you something about the mechanism of the actual underlying reaction.